Welcome to CyberXplain channel. Today we are going to discuss AI's hidden enemy, defending your models against poisoning and evasion. Vertical bar CyberXplain. Hey everyone, welcome back to CyberXplain. Grab your favorite beverage, because today we are diving into a super fascinating and increasingly critical area, the security of our AI and machine learning models. We all love the power of AI, right? But with great power comes, well, potential for some pretty tricky attacks that can make our AI go haywire. We are talking about things like data poisoning and evasion attacks. Sounds a bit sci-fi, but trust me, it's very real. Our goal today is to demystify these threats and arm you with practical defenses to keep your AI systems robust and reliable. Think of me as your friendly guide through the AI security jungle. You might be wondering, why should I care about securing an AI model? It's just code, right? Well, imagine an AI making critical decisions in healthcare, finance, or even autonomous vehicles. If that AI can be manipulated, the consequences could be catastrophic, far beyond just a system crash. We are not just protecting data, we are protecting the integrity of decisions and the trust we place in these intelligent systems. Malicious actors are getting more sophisticated, aiming to either degrade performance, inject bias, or cause specific misclassifications, and it's up to us to stay ahead. It's about ensuring AI remains a force for good, not a vulnerability. Alright, let's start with data poisoning. This is like a saboteur sneaking bad ingredients into your favorite recipe while you're not looking. In AI terms, it's when an attacker injects malicious, carefully crafted data into your training dataset. The goal? To corrupt your model during its learning phase, making it perform poorly or behave in a specific, attacker-desired way once deployed. Imagine a model learning to identify cats, but someone feeds it thousands of dog pictures labeled as cats. Eventually, it might struggle with real cats. It's an upstream attack, targeting the source of knowledge itself. Let's bring this to life with our core scenario, a medical diagnosis AI. Picture a model trained to identify cancerous cells from microscope images. A data poisoning attack could involve an adversary submitting images of benign cells, but subtly altering them to appear malignant and labeling them as benign, or vice versa, then injecting these into the training data. What happens? The model learns faulty patterns. It might start missing actual cancers, false negatives, or falsely identifying healthy cells as cancerous, false positives. This isn't just an error, it's a direct threat to patient safety, potentially leading to misdiagnosis and severe health consequences. A real-world parallel could be how easily biased data can lead to disparate impacts in healthcare algorithms. Now, let's switch gears to evasion attacks. If data poisoning is messing with the recipe, evasion is like taking the perfectly cooked meal and subtly altering it right before it's served to trick the diner. Here, the attacker targets an asterisk already trained and deployed asterisk AI model. They craft specific, often imperceptible, adversarial examples in the input data to force the model to make a wrong prediction or classification. The input might look perfectly normal to a human, but the AI interprets it completely differently. It's about finding the blind spots or weaknesses in the model's learned decision boundaries. Think about a self-driving car's vision system, a classic example for evasion. Researchers have shown how a few stickers strategically placed on a stop sign can make a robust object detection model misclassify it as a yield sign, or even a speed limit 45 sign. To a human, it's still clearly a stop sign, but the AI's neural network gets confused by the subtle pixel changes. This isn't theoretical, this has been demonstrated in labs, proving that such physical world attacks are possible. Imagine the real-world safety implications if traffic signs or pedestrians could be evaded by an autonomous vehicle. It's a terrifying thought, highlighting the need for robust perception. Okay, so how do we fight back? Our first line of defense against data poisoning is robust data sanitization. Think of it like a strict bouncer at the VIP entrance to your model's training party. Before any data even thinks about getting into your training pipeline, it needs to be thoroughly checked, cleaned, and validated. This isn't just about fixing typos, it's about systematically identifying and rejecting or correcting data that falls outside expected norms or patterns, which could indicate malicious intent or just severe errors. It's about establishing clear rules for what constitutes good data. So, what does this bouncer actually do? Data sanitization involves defining and enforcing a set of validation rules. These rules can be simple, like numeric values must be within a certain range or text fields must not exceed a certain length. But they can also be more complex, involving checking data types, ensuring consistency across related fields, or verifying data sources. For image data, this might mean checking image dimensions, file types, or even simple pixel intensity ranges. The key is to have a comprehensive set of checks that catch anything suspicious before it contaminates your model. Let's apply this to our medical diagnosis AI. For image data, like microscope slides, sanitization would involve several checks. We'd verify image resolution, ensuring it meets minimum standards, or check that pixel values fall within expected biological ranges, no pure black or pure white images unless explicitly expected. Metadata would also be crucial, verifying patient IDs, dates, and diagnostic labels against known schemas. If a batch of images suddenly has wildly inconsistent resolutions or unusual color profiles, that's a red flag. We might even check for digital watermarks or hashes to ensure image provenance if we expect data from specific, trusted devices. This careful scrutiny helps us catch anomalies that might be subtle poisoning attempts. Here's a quick peek at what a very basic data validation might look like in a Python script for our medical data. This snippet checks if a tumor_size_mm value is within a reasonable range and if the diagnosis label is one of our expected categories. Imagine this kind of logic scaled up for hundreds of features, potentially integrated into a data ingestion pipeline built on something like AWS Glue or GCP Dataflow. This simple gatekeeper prevents obvious garbage or malicious outliers from entering your precious training set, catching low-hanging poisoning fruit. Beyond strict rules, we also employ anomaly detection. This is like having an expert detective who isn't just checking for rule violations, but also looking for anything that just feels wrong or out of place, even if it technically follows all the explicit rules. Anomaly detection algorithms learn what normal data looks like and then flag data points that deviate significantly from that learned norm. This is super powerful for catching more subtle poisoning attempts where an attacker might try to introduce data that's technically valid but statistically improbable or highly unusual. It's about statistical outliers and deviations. There are several cool techniques we can use for anomaly detection. Simple statistical methods like z-scores or IQR, interquartile range, can flag values far from the mean. More advanced methods include clustering algorithms like k-means, where data points far from any cluster centroid are anomalies. Isolation forests are also popular, as they isolate outliers by randomly partitioning data. And for high-dimensional or complex data, we might use autoencoders, neural networks that learn to reconstruct normal data and flag data that's poorly reconstructed. Each method has its strengths, and often, combining them gives you the best coverage. Back to our medical AI. Imagine we receive a batch of chest X-rays. Anomaly detection might flag an image with an unusually high pixel intensity range, potentially indicating digital manipulation, or an X-ray where the patient's heart is on the wrong side, a rare but natural anomaly, or perhaps a sign of data corruption if it's consistently mislabeled. For numerical data, an anomaly detector might highlight a patient's lab result like blood pressure 300 by 200. It's numeric, but physically impossible for a living human, flagging potential data entry errors or malicious inputs. This proactive flagging gives human experts a chance to review before it poisons the model. While incredibly powerful, data sanitization and anomaly detection aren't without their trade-offs. Overly strict rules might lead to false positives, where perfectly legitimate but rare or unique data points are rejected, potentially limiting the model's ability to learn from diverse cases. This could be particularly problematic in medical contexts where rare diseases might present as anomalies. On the flip side, rules that are too lenient will let malicious data slip through. There's a constant balancing act between being too restrictive and too permissive, often requiring domain expertise to tune. It's an ongoing process, not a one-and-done solution. Even with the best data sanitization, some clever attackers might still get through. So, our next line of defense is to make our models inherently more resilient and tougher during their training phase. This is where robust training techniques come in. Instead of just passively learning from the data, we actively challenge the model during training to make it less susceptible to small, adversarial perturbations. We want to build a model that doesn't crumble at the slightest trick, one that has learned to generalize better and be less brittle. It's like sending your model to a cybersecurity boot camp. One of the most effective robust training techniques is called adversarial training. Here's the cool part. We intentionally create adversarial examples during the training process and feed them back to the model. We are essentially showing the model, hey, this is how someone might try to trick you, so learn to recognize and resist it. It's a continuous cat-and-mouse game within the training loop itself, where the model learns to correctly classify not just clean data, but also data specifically designed to fool it. This makes the model significantly more robust to evasion attacks once deployed. Technically, adversarial training often involves generating adversarial perturbations using techniques like FGSM, Fast Gradient Sign Method, or PGD, Projected Gradient Descent. During each training step, we calculate the gradient of the loss function with respect to the input data. This gradient tells us which direction to nudge the input pixels to maximally increase the error. We then create a perturbed version of the input, add it to our training batch, and train the model on both the original and the perturbed examples. It's like teaching the model to see the subtle trick features and not be fooled by them. Many frameworks, like TensorFlow and PyTorch, have libraries that facilitate this. For our medical diagnosis AI, adversarial training would mean generating subtly altered microscope images that are designed to trick the model into misclassifying benign cells as malignant, or vice versa. For example, slight, almost invisible pixel noise or pattern shifts could be introduced. The model would then be trained to correctly identify the original label for both the clean image and its adversarial counterpart. This makes the diagnostic AI much more resilient to subtle manipulations or noise in real-world clinical scans, reducing the chances of an attacker causing a misdiagnosis with a cleverly crafted input. It makes the model's decision boundaries more robust. Beyond adversarial training, other robust training techniques also play a crucial role. Regularization methods, like L1 or L2 regularization, also known as weight decay, help prevent overfitting by penalizing large weights in the model, forcing it to learn simpler, more generalizable patterns. Dropout is another common technique where during training, random neurons are temporarily ignored. This prevents co-adaptation and forces the network to learn more robust features. These methods, while not specifically designed for adversarial attacks, generally improve model generalization and, as a side effect, often enhance robustness to minor perturbations. They contribute to a more stable model overall. Robust training, particularly adversarial training, comes with its own set of trade-offs. The biggest one: computational cost. Generating adversarial examples on the fly and training on them significantly increases the time and resources needed for training. Also, models trained adversarially might sometimes have slightly lower accuracy on clean unperturbed data compared to models trained traditionally, though they perform far better on adversarial examples. It's a balance between robustness and raw accuracy. For critical applications like medical AI, the increased robustness often outweighs the slight drop in clean accuracy and the higher training cost. It's an investment in safety. Let's explore another cool technique, defensive distillation. Imagine you have a complex, highly accurate teacher model. What we do is train a simpler student model to mimic the predictions of the teacher model, rather than directly learning from the raw data labels. The student model learns the soft probabilities from the teacher, example, 80% chance of malignant, 20% benign, instead of hard labels, malignant. This process smooths out the decision boundaries of the student model, making it less sensitive to small input perturbations and thus more robust against evasion attacks. It makes the model less jumpy and more stable. Here's how it generally works. First, you train your powerful teacher model on the original dataset. Once that's done, you use this teacher model to predict probabilities for all your training data. These probabilities, not the original hard labels, become the targets for training your new, smaller student model. The student model learns to reproduce these smooth, nuanced predictions. This regularization effect of learning from a softened target often makes the student model less susceptible to the subtle, targeted changes of adversarial examples, as its decision surface is less jagged. It's a way to transfer robustness. Next up are ensemble methods, basically, the wisdom of the crowd applied to AI. Instead of relying on a single model, we train multiple, diverse models to perform the same task. When it's time to make a prediction, all these models weigh in, and we combine their outputs, perhaps by averaging their probabilities or using a majority vote. The idea is that an attack designed to fool one specific model might not work on the others, especially if they have different architectures or were trained on slightly different data subsets. It adds a layer of redundancy and makes the overall system much harder to fool. Think of it like a security team with diverse skill sets. Common ensemble techniques include bagging, like random forests, where multiple decision trees are trained on bootstrapped samples of the data, and boosting, like gradient boosting machines, where models are trained sequentially, each correcting the errors of the previous ones. For deep learning, we might train several neural networks with different initializations or slightly different architectures. When an adversarial example tries to trick one model, the others are likely to correctly classify it, and their collective vote helps override the single-fold model. This collective intelligence significantly boosts the overall robustness against evasion attacks. For our medical AI, combining these methods offers powerful protection. Imagine a diagnostic AI where an ensemble of 5 different models, each potentially trained with some adversarial examples and then further refined via distillation, review a single patient's scan. If an attacker tries to inject an adversarial pattern into the scan to trick one model into a false positive, the other 4, with their slightly different learned patterns, are likely to catch it and vote correctly. The final diagnosis, based on this collective wisdom, would be far more reliable and resistant to both subtle evasion attempts and noise, ensuring higher patient safety. This layered approach is key. Even after all these sophisticated training methods, we still have a final gatekeeper for incoming real-time data, input preprocessing and filtering at inference time. This is where we apply many of the same sanitization and anomaly detection principles we discussed for training data, but now to every single input that goes into the deployed model. Think of it like a last chance checkpoint. We normalize data, remove irrelevant features, and apply basic sanity checks. If an input looks like an adversarial example, perhaps it contains pixel values outside the expected range or statistical anomalies, we can flag it, quarantine it, or refuse to process it, instead of feeding it directly to the model. This is critical for preventing evasion attacks from reaching the core. For our medical AI, This means that every single diagnostic image submitted by a doctor or clinic goes through a battery of checks before the model sees it. We'd quickly check for valid image formats, expected dimensions, and perhaps run a simple statistical analysis on pixel intensity distribution. If an image is flagged as potentially manipulated, say, by having unusual noise patterns that don't match typical scanner artifacts, it's immediately sent for human review. We wouldn't just trust the AI with potentially compromised input. This ensures that even if an attacker manages to craft a clever evasion example, it gets caught at the edge before it can influence a patient's diagnosis. This is a crucial practical step in a production environment. Our final defense isn't a single technique, but a continuous process, active monitoring of your deployed model. Just like you monitor your network for intrusions, you need to monitor your AI model's performance for drift and unexpected anomalies. Data drift means the characteristics of your incoming live data start to change significantly from your training data, which can degrade performance and open new attack vectors. Concept drift means the relationship between input and output changes over time. By tracking key metrics, input distributions, and prediction confidence, we can detect unusual behavior that might indicate an ongoing attack or a degradation that makes the model more vulnerable. This is crucial for long-term AI health. Phew! We've covered a lot today, from data poisoning to evasion attacks, and a whole arsenal of defenses. The key takeaway here is that there's no single magic bullet for securing AI. Instead, it's about building a multi-layered defense strategy, strong data sanitization and anomaly detection upfront, robust training techniques to build resilient models, defensive distillation and ensembles for added stability, rigorous input filtering at inference, and continuous monitoring. Think of it like fortifying a castle, with walls, moats, guards, and watchtowers. Each layer strengthens the whole. By implementing these practices, we can significantly increase the trustworthiness and resilience of our AI systems, ensuring they continue to serve us safely and effectively. Thanks for joining me on this deep dive, and I'll catch you in the next one. Thanks for watching. Subscribe to the CyberXplain channel. See you on the next video.